Hello, everyone. Today, our talk is mainly on the community updates for OVS and OVN side. Along with me, I have Ionut from Cloud-Based Solution, as Ben already mentioned, and Saram is at the backstage. Unfortunately, Alan Serdean from Cloud-Based was not able to make it to the conference. We would like to take this opportunity to thank him for preparing the demo and recording the demo and sharing it, which will be presented at the end of the presentation. So what do we have here? So today, we'll be basically talking about updates on the OVS side. So we'll briefly go over the solution, like what we have implemented for what we have a solution for Hyper-V, and we'll briefly go over the architecture of OVS on Hyper-V, and then we will list out the features that we currently support, and then briefly talk about the containers. And Ionut will be continuing with the presentation and talk about the Kubernetes. And finally, we'll have a demo on the Kubernetes. So OVS as a solution, this approach was started. This effort was started back in 2014. This was done as a collaboration effort between two companies, VMware and Cloud-Based. As a part of this effort, there were two major tasks, you can say. One was like porting the existing Linux user space code so that they can be run easily on Windows. And the other one was implementing a brand new Windows data path. So this was basically, we had to come up and write a new NDIS-based driver, which is nothing but a Hyper-V forwarding extension driver. So let's walk through the architecture. So on the architecture side, you can say we can briefly divide the components into two parts. One is the Hyper-V components, where Hyper-V actually provides a virtual switch for the third-party vendors. It provides some extensions for the third-party vendors who can actually attach to this virtual switch and do packet forwarding decisions or even do basic packet monitoring operations on that. And the other major component is the OVS component, as I previously told, which contains OVS user space and OVS vSwitch. On the user space, basically, we have OVS DB server and OVS vSwitch and all the utilities that lie like OVS app kernel, OVS TP kernel that are run on the user space. And apart from that, on the kernel side, we implemented a OVS ext driver, which is nothing but a packet forwarding extension driver, which attaches to the Hyper-V switch. In order to leverage the existing implementation for user space and kernel communication, that is DPIF and a netlink interface. So on the Windows, Windows currently doesn't support netlink interfaces natively, netlink sockets natively. So we had to implement this netlink messages on the data path side. And netlink parser, we had to implement netlink parser on the data path side so that user space basically can communicate with the kernel Windows data path. In the next slide, I'll be basically going through the packet flow where we have architectural diagram, so which will have a better understanding on that. One thing I would like to highlight is that on Windows, we call each packet is represented as a net buffer list, which is nothing but an NBL. This is similar to the socket buffer that we have on the KVM side. So let's go. As I mentioned previously, you can see on the right-hand side, we have a Hyper-V component, which actually Hyper-V component. So on the Hyper-V, basically, it provides a Hyper-V extensible switch, which third-party vendors can actually attach to it. And on the left side, you can see the OVS components. On the top left, you can see the user space components that we support that are been running, and on the bottom we see the kernel driver that is implemented. As you can see, when we attach to the virtual switch, we basically register ourselves as a forwarding extension on the Hyper-V switch. What this means is that we register for the callbacks for the management of the ports in the switch. We register for the callbacks whenever a packet is being received, so that we can make forwarding decisions on that. Let's walk through the packet flow. So the packet enters the Hyper-V switch on the ingress pipeline from the VM, and the Hyper-V switch forwards this packet to OVS in order to decide what to do with this packet. So on the Windows data path, basically we extract the flow key, and then we do a flow-based lookup. If a corresponding flow, if there is no matching flow, then we send the packet to the user space. So user space basically computes looks through the flow table and computes the flow for this, and programs the necessary action, and sends the action and sends the flow along with the action to the data path. On the data path, the action can be very simple, like sending it to a specific port on a VM, specific port, or it can have complex actions like executes contract actions, or setting a particular header, or something like that. So once we have this information, we add this forwarding information into the net buffer metadata itself, and then send the packet back to the Hyper-V switch. So the Hyper-V switch finally sends the packet out to the corresponding destinations through the egress pipeline. It can be another VM on the same host, or it can be sent out to another host through the physical link, as mentioned here. So coming to the features, so when we started implementing this solution, initially we added support only for Windows Server 2012 and 2012 R2. Then later on we added support for Windows Family 10 as well. So very recently we even tried installing OVS on Windows Server 2019, and we were able to install it cleanly, and OVS seems to work reliably on that. Apart from that, looking at the feature set, we support most of the flows and actions that are supported on the KVM. We support the major tunneling protocols like GRE, Jenny, STT, and VXLAN. Even we support hardware offloads as well. Windows does not have connection tracking, so we had to implement our own connection tracker on the Windows datapath to support the stateful firewall. We have support for multiple NICs. We can have multiple tunnels. We can leverage the NIC bonding as well. So regarding the containers, so Windows started supporting containers since Windows Server 2016 or the Windows 10 family. So how it provides the networking for the containers is basically it creates an internal switch, which is internal virtual switch, which is similar to the Hyper-V switch that I already spoke about. So OVS binds to this particular switch to make the packet-based forwarding decisions. That's how OVS works on containers. So looking at the recent changes that we made, for the past couple of years, we have basically been working on stabilizing the driver. So we did a lot of testing internally, and whenever we identify any particular issue, we file an issue and then fix that as soon as possible. So currently, the Windows data path is in a very good, stable state, you can say. Apart from that, we added a couple of features on the contract, notably like NAT feature and IP, adding support for IP fragments. So since OVS 2.8, I think we have support for NAT and IP fragments. And very recently in OVS 2.10, we added support for zone limits. Apart from that, we did a bunch of performance optimizations and contract for a particular connection. We also have continuous integration with some of the unit tests running for the user space changes. We have sent out a patch for enabling support for host network stack APIs. So this basically enables us to work with the containers seamlessly. So looking at the roadmap, we have a couple of features that we want to implement in the future. One major thing is we want to look into adding support for PCAP interfaces. So this will help us to move away from the Hyper-V limitation. Mega flows and the UFIDs are other major items that we have planning to add in the next future. Regarding IPv6, most of the OVS for Hyper-V actually supports IPv6. So we are lacking only in the contract and tunneling. So I think we'll be taking that sooner. And we'll also be adding support for other tunnels as well. So now I'll hand over to Ayat to continue with the presentation.
Thank you very much. So OVN in Kubernetes. OVN works with both containers and virtual machines, and it supports Docker and Kubernetes. But for this particular presentation, we'll be focusing on the Kubernetes use case. So we'll emphasize a particular project called OVN Kubernetes, which is maintained by Open vSwitch contributors, and it simply implements the Kubernetes CNI specification to add, remove, and check network adapters to containers. It works with overlay model. That means you're able to create a logical network amongst containers on different hosts, and they can communicate with each other. We use daemon sets for an easier deployment. That means from a sysadmin perspective, deploying, upgrading, and everything else, it's easier since all the daemons are running inside containers. HA for OVN, it's available since OVS 2.10. So how do you deploy OVN Kubernetes project? So for small deployments and testing clusters, you have Vagrant setup scripts. Those simply support only Linux-only clusters. If you would like to check out a hybrid cluster, the one that we prepared for the demo today, with both Windows and Linux, you can simply use the Ansible playbooks that we submitted upstream. It has meaningful reviews, so feel free to check them out, provide any feedback, or open any issues. So what are the benefits of using OVN Kubernetes? Well, you get out of the box all the goodies that come with OVN inside your Kubernetes clusters. You get distributed firewalling for your pods with containers. It can be used with service meshes, Istio or AWS service mesh, for instance. And you get full heterogeneous deployment support with Windows and Linux, and on-prem and off-prem deploy nodes with IPsec support via OVN for encryption. And you already saw that in the previous presentation. Thanks for the awesome work. And OVN Kubernetes is already heavily used in mixed environments since Windows Alpha support was officially announced in Kubernetes. OpenShift Tech Preview from Red Hat, starting from version 3.9, already supports OVN Kubernetes environments with both Windows nodes. So what is the future work that we prepared for OVN Kubernetes? Well, for now, the implementation of OVN Kubernetes heavily relies on exec calls. So the need for some Golang bindings is necessary. There is a work in progress branch that I just linked into the slide that will be submitted upstream. We would like to add integration with KEOPS and KubeSpray. And on top of that, adding Kubernetes operator for OVN Kubernetes. And last but not least, we would like to add more features and improve our Ansible playbooks and Vagrant setup scripts.
Excuse me, sorry.
So coming back to the demo environment, I have a simple diagram prepared for you just to get a better understanding about what we prepared. So when you start deploying Kubernetes, a typical small deployment will consist of a master and a minion. We went into the Azure portal, we created 2 virtual machines, configured one of them as the Linux master and the other one as the Linux minion. Just for the sake of diversity, we went into the Google cloud, created a Windows VM, and simply configured that with Kubernetes and connected that to our existing Kubernetes cluster. Just because we remember that AWS is preferred by some customers due to the performance of their Linux VMs, we went into the AWS portal, created the Linux VM, and simply hooked that up with our existing Kubernetes cluster. But we remember that back at home, we have an on-prem hardware that is simply doing nothing, so why not use that with a Windows VM on top of it and connect it to our cluster? So we did that as well. And we remember that there is still an option to the public clouds, DigitalOcean, and right now, officially, they do not support Windows instances, but they added the option to have custom images in their cloud. So due to some work that cloud-based engineers did, adding support to the DigitalOcean metadata to the cloud-based init agent, you are able to simply get a Windows VM with a custom image that generate. That's how we got Windows agent in Kubernetes into DigitalOcean Cloud. And simply configured with Kubernetes and connected it to our cluster. So in essence, this is the demo environment that we have. We deployed pods so that we have a container into each minion. That container, it's using an image that has a simple web server, which upon request will return the host name of that host where the container is actually hosted. So this will let us simply execute some commands and get the host name of the actual minion. We'll be simply demoing some internal load balancing, yeah, and also, we would like to demo some external load balancing as well, because we configured all the nodes as gateway nodes just for the sake of this demo. So let's get back to the demo. So I will start with the basics. I will open the shell console into each agent, and I simply go and type host name just to get an insight what's behind there. So I have meaningful host names for each agent. Yeah? And to get a stronger belief what's behind, there are some CLI commands that I execute just to get some information about the underlying hardware of the virtual machine. Into the Azure virtual machine, I get some Microsoft branded hardware that is used in Azure for the hypervisors. For my on-prem node, I get some Hyper-V on-prem hypervisor that I used back at home. And of course, for the Google Cloud and for the DigitalOcean, I get labeled Google and of course DigitalOcean. So what I'm going to do next is go back to the Kubernetes CLI and check if the API reports all the nodes are available. Of course, they are all ready and nice, and I'll go and check the containers. Containers are up and running. They are reporting successful status, and I'm trying right now just to get the internal load balancer IP and port and the external load balancer IP and port from the OVN northbound CLI. I fetch those, and initially, I go into the minion and do a curl for every private IP address behind the load balancer, just to see what response I could get when, after that, I will simply run a loop and curl the load balancer. By doing that, on every response to the curl against the load balancer, I will get a different response. That means the request is load balanced across all my nodes that, remember, are running into be it Azure, AWS, DigitalOcean, and on-prem. Just to show that Windows is no other than Linux, and it's a first-class citizen, I will go and execute the same loop for the Windows nodes. And I'm seeing the same behavior. What I'm going to do next is try and demo some external load balancing. So I'm going into my local machine, open up a browser, and I will try and fetch the public address of each individual minion and simply try and see if I get any response. Ideally, I should get the same response that I'm getting when querying the internal load balancer, as you see right now. I just give a little bit of time just to see that every response possible is available. And now I'm trying the same, but instead using the public IP address and the external load balancer port. And at every refresh into the browser, I get a different response, meaning that the request was coming from a different host. So yeah, this is it. This is the actual demo. It's a Kubernetes deployment with nodes running across multiple clouds on-prem and running under the same Kubernetes master using the same OVN controller. So here I have some useful links in case you want to check them out. And shout out to the meeting that we have on Tuesday at 10 a.m. into the IRC channel, and we're happy to take any questions.
Well, we have time for questions, so come on up to one of the mics.
I have a question about the when you have packets processed in the kernel, by the Hyper-V vSwitch, and then you use your forwarding extension to send packet up to user mode for OVS processing. Have you solved any issue with the user mode thread being preempted by higher priority kernel process?
So you're essentially asking if there are multiple packets coming out of the forwarding extension, and while the user space is working on computing the next action, if a packet gets preempted, is that your question?
Yeah, so while you process packets in user mode, packets keep coming in from the next, right?
So the way we handle packet processing inside OVS is once we get a packet from the OVS extension inside OVS, if we determine that a particular packet needs to get punted up to the user space for computing the next action, we just complete that NBL, and then we create a new buffer or a clone of the packet and send it up to user space. That way we don't hold on to that packet or the memory of that.
But meanwhile, there are more packets.
Yes, there would be
coming
more packets.
in.
Yeah, exactly. So we have a queue.
Mode.
We have a packet queue that we implement, and then every packet that needs to go up to user space will get cloned over and then sent up to the user space. And once vSwitch computes the next flop, it will then push it back in. It will be a completely new packet.
But how do you prevent the user mode thread from being starved by the kernel mode processing of,
So we haven't-
interrupts coming in from the next,
So
with
we
more
haven't
packets.
actually had any issues with that.
Okay. Even at like line rate processing?
Yes.
Oh, okay. That's it. All right, thank you.
Thanks. You had Golang bindings for OVN. I didn't see what the link was. I assume, is that the code that Tom's Attica had been working on to do the Golang bindings?
So as far as I know, there is some work in progress by Guru. I'm not exactly sure the branch.
Okay, yeah, I think that was with Tom's. I just want to make sure there wasn't
Yeah.
another project too, like that there weren't duplicate ones. Great, thank you.
No problem.
We have time for more questions if anybody would like to ask one. All right, let's thank our speakers.